Linear transformations. Linear transformation is the process wherein a matrix is multiplied by a vector or a scalar quantity, and when the matrix is multiplied by a scalar or a vector, then its dimensions are changed or its values are going to be changed. So to see regarding these, let's learn the four transformations that come from matrices. The first one is multiplication by a scalar, rotation, reflection, and projection. So to know these, let's see. The first one is multiplication. Let's consider a scalar quantity, and on the scalar quantity, if a scalar quantity is multiplied with an identity matrix, then we'll get an identity matrix is multiplied by a constant. Let's say it is C. If the identity matrix gets multiplied by C, then we'll get C 0 and 0 C. Then a vector, we know that it is a two-dimensional space. As it is a two-dimensional space, let's represent any of the point here. Let's say it may be a 0 1. If 0 1 is to be represented, we know horizontal axis is x, vertical one is y. So 1 0 is represented on the x-axis. Let's say here 0 1 0. Or if it is a 0 1, it will be on the y-axis, or if it is any middle value like 1 1 or 1 2, then it will be in between both the axes. So let's say xy is our point, then we join it to the origin. This represents our xy vector. When this gets scaled by a value, then its dimensions are going to change. If the value of the c is greater than 1, if the scaling factor is greater than 1, then our vector is having a resulting vector after multiplication will have more the length than the original one, or it expands, we can say. It may be in whichever the dimension. And if the c is less than 1, then this vector will be compressed, or we can say it will be reduced in its length. So the same we can say the whole space expands or contracts depending upon the value of c. And if the c is negative, then even this vector, if it gets multiplied by -1 and so on, -1 value, then it may project in the, or it may be directed in the other direction, or in the minus reverse direction. Then the next thing is the rotation. To learn this rotation, let's see this point. So the rotation can be learned by considering this. So in rotation, we consider, let's consider a rotation. Let's see the rotation. So in case of rotation, we'll be considering a unit matrix, and this unit matrix will be what? So before that, a rotation is nothing but rotating the point or rotating the column vector, whatever the dimension we are dealing with or we are considered, by 90 degrees. So transforming every point xy, let's say in two-dimensional, to 90 degrees by 90 degrees. So xy may turn as minus yx, or it may be xy itself. Let's see what all are the conditions to understand how the rotation gives this matrix. Let's see this example. Now let's take the unit matrix, the identity matrix of 2 by 2 order. Now the first column is 1 0. This first column 1 0 is represented here. X is 1, y is 0. So 1 0 will be represented in this way. As 1 0 is represented here, now let's represent that point. Now during rotation we'll be moving this point by 90 degrees. Let's say we move it by 90 degrees. When we move it by 90 degrees, then the next location of that point after moving, after rotating, is this one. And if there is a point here, it will be given by 0 1, because it is on the y-axis. On the y-axis the value of x is 0. So after rotation, this identity matrix will turn to as 1 0 will become 0 1. Let's see what this 0 1 will turn as. Now 0 1 places here, let's draw it a bit upper. It is exactly at this place itself, just not to overlap. So this is our 0 1. 0 1 is on the y-axis. Let's use this as 0 1. Now when this gets rotated by 90 degrees, then it will fall, or it will go to y-axis. It will go to x-axis, that to negative. So the next place of this second point, the second column, is how we represent a point at this place. So this point will be given by, this point will be represented by, it is -1, x has to be written first, -1 and 0, -1 0. So this will 0 1 will turn as -1 0. So this is the way in which we obtain the rotation. A rotation of a matrix is obtained in this way. Every vector is rotated by 90 degrees. Next one is the reflection. The reflection matrix is obtained by reflection. So here what we do is we draw a two-dimensional plane and a line of 45 degrees with the x as well as y axis is drawn. Then reflection means mirror image. Consider a point anywhere on the axis, then the mirror image of that point about that line, by considering that line as the axis, whatever is the mirror image of that point will be the next point, or it is the whatever is the mirror point of that one is there, the dimensions of those, that point are nothing but, or the values of that point are nothing but the rotated values of that vector, column vector, or it can be a column space or a row space. Now to understand this one, so what we do is we draw a line making 45 degrees angle and wherein y is equal to x. So let's consider that one. So we consider in this way and we draw a line. We draw a line this way. Now let's take this line which is y is equal to x. Now let's take the point 1 1. What is the reflection of this point? Now 1 1 means a value, its value is 1 in x direction as well. Its value is 1 in the y direction. When we go for intersection of these two, so it will be at this place which will lie on the line. If the point is lying on the line, then the reflection of that point would be the same itself. Means the reflection of this 1 1 is 1 1 itself. It is 1 1 itself. Similarly 2 2. If the point is 2 2, so it will be lying on the line and its reflection is 2 2 itself. So it applies to all the values wherein y is equal to x, even in the negative direction. If -1 is considered, it will lie at this place and its reflection is -1 itself. Now let's take the point wherein x and y are not equal. If we take up the point as shown here, it is 2. Let's take 2 minus 2. If we take 2 and minus 2 means on this side, let's say this is 1 and 2 here. So the point will be lying at this place. The reflection of this 2 minus 2 is when we move this when exactly the mirror image will fall at this place, wherein the 2 and 2 will intersect. But this point is given by the values. Its value x is negative. Of course it has to be 2. So the reflection will be minus 2 and the other dimension y is 2. Now when we have a reflection of 2 minus 2, we'll get minus 2, 2. If the point is considered at this place, then its reflection will lie at this place. If the point is here, then its reflection will be here. If it is here, then certainly it would be just on this side, like. So this is the reflection. The next one is projection. What is projection? The projection means the matrix takes the whole space into a lower dimensional subspace. Not invertible, the example transforms each vector xy in the plane to the nearest point x0 on the horizontal axis. Means, now I hope this reflection is understood. Reflection of, let's go with this as we have not done. Reflection of 1, 0 is reflection of 1, 0. 1 will lie here and 0 will be there. Reflection of 1, 0 will be 0, 1 and reflection of 0, 1 will be 1, 0. Okay, now let's go for this projection. The projection is lowering of one dimensional, or we can say here we consider one of the dimension to make it as 0. Now here we are taking a point. Now let's go for this. Let's say the point is xy. Then how do we represent? The point xy will be represented in this way. It will be, let's say it is x is 1 and y is also 1. So this point is, let's say 1, 1. Then what we do here is we cancel one of the dimension. Usually x is our first dimension, so we try to cancel the second, that means y. We represent this xy itself as 1, 0. We make this other dimension 0. Similarly, if the point is, let's say 0, 1. If the point is 0, 1, then it has to be represented on the y-axis, but we have decided to make y as 0, means it will be that 0, 1. In place of representing here, we consider it as 0, 0. If we are representing 1, 0 only, then no problem, it will be represented as it is, because other axis is 0 by default, so it will be represented at this place. So projection means lowering, or usually the last dimension is made 0. By making the last dimension of our last value as a 0, we are getting another kind of a space that is nothing but one value lower in dimensional subspace, or it is a space. So that is projection. So once we understand these all operations, next thing is operation or learning of the polynomials things. So let's take up a polynomial. Let's say the polynomial is, we all familiar with a0 plus a1t plus a2t square and so on up till an t raised to n. So we need to learn the linear transformations with respect to these polynomials. So before this, let's see the properties of linear transformation. As it is not a new thing, we know linear transformation means just like the vector space. It has to satisfy the addition and multiplication rules. So if A is a matrix or A is anything, then Cx plus dy, where C and D are constants and x and y are the vectors. When the A matrix gets multiplied, for the subject it has to be A. When A has to be a matrix, then we'll get Cex plus D into Ay. So if it is true, then every transformation T of x that meets the requirement is the linear transformation. Every transformation that satisfies this one will meet the linear transformation, or we can say it is linearly transformable. Example is the operation of differentiation. Now we want to check whether the differentiation operation is linearly transformable or no. So to check that one, consider this polynomial and A of pt. Now P of t is as equation and A is our differentiation operation. When A, that is differentiation operation, is operated on our polynomial, then we know how to do the differentiation. Differentiation of a0 has to be 0, otherwise the rest of the a1t is there, differentiation of t is 1. Likewise, when we go for differentiation of these entire terms, we'll get a1, only first one gets cancelled, the rest all will be as it is, a1t plus a2, a1t will be converted into a1, second one is a2 t, it would be in this way. Then for this, the null space of this A is one dimensional space of constants dA naught